It glints from our rooftops and soars through our skies, a silent testament to our modern world. Every year, our global appetite consumes a staggering 68 million tons of this versatile material, weaving it into everything from the humble beverage can to the vast wings of commercial airliners. To meet this colossal demand without depleting the earth, industry turned not to the ground, but to a revolutionary cycle of renewal. Through the elegant process of recycling, discarded aluminum begins its journey back to life. The collected scrap is first sorted and cleansed of impurities, then returned to a molten state in fiery furnaces before being cast into new forms. This remarkable loop saves an astonishing 95% of the energy needed for primary production, allowing the metal to be reborn in as little as 60 days, its quality perfectly preserved for its next life. It can be crushed in a moment, yet its essence can endure for centuries. While other metals weaken with every reuse, aluminum possesses a remarkable secret. It can be reborn again and again without a hint of degradation. This incredible resilience is why nearly 75% of all the aluminum ever smelted is still circulating through our world today. The United States has harnessed this cycle, building an industrial power from what was once discarded. Through a vast and efficient network of collection and smelting, reclaimed aluminum now satisfies over 1/3 of the nation's yearly demand. This process yields a staggering 95% reduction in energy compared to creating new metal, liberating enough power to sustain millions of homes. Beyond the economic advantages lies a profound environmental dividend, reinforcing the nation's leadership in sustainable industry. For each ton of aluminum that is reclaimed, the atmosphere is spared the burden of up to 9 tons of CO2 emissions. Annually, this translates into tens of millions of tons of greenhouse gases that are never released. This inherent efficiency is becoming ever more critical. As the country accelerates its transition toward electric vehicles, wind power, and solar energy, this lightweight, endlessly reusable metal stands as a cornerstone of a new, energy-conscious industrial age. From a million different hands, it all converges here. A simple can begins a journey that defines the efficiency of everything to come. In the United States, a global leader in aluminum recovery, an intricate collection network sprawls from coast to coast. It weaves through beverage can redemption centers, municipal sorting facilities, and vast industrial scrap markets. Every year, this system gathers tens of millions of tons from innumerable sources, creating a ceaseless river of metal that feeds the nation's recycling apparatus. The powerful engine driving this entire process is pure economics. A single discarded aluminum can holds a value many times greater than a plastic bottle, creating a compelling reason for both people and companies to guide it back into the production loop. This financial incentive is why America consistently achieves high recovery rates, securing a stable domestic supply of recycled material for its industries. From these collection points, convoys of trucks make their way to immense staging yards. Upon arrival, each vehicle is meticulously weighed and its contents logged before it tips its payload onto conveyors destined for the storage area. Here, beer cans from stores, food trays from homes, and scrap from industry merge into towering, shimmering mountains of raw material. On the ground, technicians conduct swift preliminary inspections, their trained eyes scanning for contamination. Any load containing too many impurities or hazardous substances is immediately flagged and turned away. The pace is relentless, with thousands of tons of aluminum pouring in daily, making this yard the critical gateway where all incoming metal is marshaled for a more precise phase of sorting. Inside the processing facility, the stream of scrap flows onto long, constantly moving conveyor belts. A battery of optical sensors acts as electronic eyes, scanning thousands of fragments every second to identify aluminum by its unique color and its distinct reflection of light. Immediately after, A powerful magnetic field plucks any stray ferrous metals from the stream, while precisely timed jets of air blast the aluminum away from plastics, paper, and other debris. Through these multiple layers of separation, the once chaotic jumble of material is gradually refined into a uniform flow of glinting silver. Now chemically consistent and tightly controlled, the purified aluminum is ready to advance deeper into the heart of the recycling process. The air shudders with a metallic scream, a sound of violent rebirth. Once isolated, the aluminum scrap is devoured by a massive shredding system. Conveyor belts relentlessly deliver a torrent of beer cans, food trays, and industrial offcuts into the maw of counter-rotating steel rollers, each lined with hardened teeth. The metal shatters on impact, its sharp percussive echoes ringing across the factory floor. Within just a few revolutions, hundreds of kilograms of aluminum are pulverized into small, uniform fragments. This mechanical dance is assisted by rotating blades and crushing hammers, enabling the system to tear through even the thickest, most rigid aluminum parts. Under the harsh glare of industrial lights, a continuous cascade of silver shards pours onto a lower belt, glittering like a metallic river. A vibrating screen system then sifts the output, guaranteeing every piece is reduced to a consistent dimension. This creates a stable, uniform feedstock, perfectly prepared for the next stage of its transformation. From here, the shredded fragments are conveyed directly into industrial furnaces, the fiery heart of the entire recycling operation. Depending on the scrap's origin and its intended final use, the facility might employ reverberatory furnaces, rotary kilns, or electric arc furnaces. Each is a sealed feat of engineering, meticulously designed to manage three critical variables at once: temperature, airflow, and the rate of material mixing. The internal temperature is held in a precise range, between 660 degrees and 750 degrees Celsius. This is just enough heat to melt the aluminum without vaporizing its valuable alloy components. Material is loaded through a top hatch or a tilting chute, then continuously agitated by either mechanical paddles or controlled injections of air. Some furnaces are even fitted with heat recovery systems to maximize energy efficiency, while multi-stage filtration units scrub the exhaust, capturing aluminum oxide dust and neutralizing toxic gases. Throughout this smelting process, thermal sensors and chemical analyzers act as the system's senses, operating without pause to ensure every batch of molten metal meets exact technical specifications. The furnace represents a climactic convergence of pressure, heat, chemical reactions, and mechanical force. A single error in control could render an entire batch useless, but when all elements work in harmony, the result is a flowing stream of pure, liquid metal ready for the next phase. Even after the aluminum has completely liquefied, it still harbors countless impurities invisible to the naked eye. These hidden contaminants include aluminum oxides, furnace dust, paint residues, and even oils left from its former life. To purge them, the plant initiates a refining process directly inside the furnace itself. The most common method involves adding a special fluxing agent to the molten bath. As the flux reacts, it binds with impurities, forming a light, foamy dross that floats to the surface. This layer is then carefully skimmed away, leaving cleaner, more refined metal behind. In more advanced systems, inert gases like argon or chlorine are injected at low pressure. These microscopic bubbles permeate the molten mass, trapping excess oxygen and hydrogen and carrying the unwanted elements to the surface for removal. This entire purification process unfolds under the constant watch of temperature sensors and control systems, ensuring the molten aluminum achieves the purity required for the stages to come. The metal's chaotic dance is over. Now, it must find its shape. Having reached the necessary purity, the molten aluminum is channeled toward the casting area to begin its physical transformation. This is the crucial transition from a formless liquid into a structured solid, a measurable unit ready for transport and processing. The shimmering metal pours into molds made of steel, graphite, or specialized heat-resistant composites, their material chosen for the final product being formed. These may be vertical molds that shape ingots, horizontal ones for thick slabs, or continuous casting systems that use water cooling for forced solidification. Every detail, from the pouring speed and mold temperature to the intensity of the cooling, is precisely calibrated. A pour that is too rapid can trap gas pockets or introduce surface cracks, while a mold that is too cold risks uneven solidification, creating hidden structural flaws deep within the metal. Each parameter must be perfectly balanced, like guiding a powerful current through a narrow channel, as the slightest deviation can distort the entire product. In many modern facilities, this delicate process is fully automated, with sensors continuously monitoring pouring height, cooling rates, and surface temperatures. Yet in some semi-manual lines, the control still rests in human hands, a task demanding sharp instincts and split-second precision from skilled workers who command the flow. A faint red glow still clings to its surface, a memory of the fire within. Once the aluminum has solidified, a hydraulic system pushes from the bottom, gently releasing the solid metal from the steel mold walls. Mechanical clamps descend to grip the heavy ingot, which can weigh dozens of kilograms. It is lifted from the casting trough and placed onto a parallel steel conveyor, the sound of scraping metal echoing throughout the foundry. In perfect sync with the machinery, the ingots are extracted one by one, lining up neatly on the moving belt. As they proceed, sensors quickly scan each piece, checking its shape and dimensions for any deformation. From the casting area, these rows of solid aluminum begin their steady journey forward. Aligned like metal bricks, their procession marks the completion of a full production cycle inside the furnace. The journey from a solid mass to a shimmering ribbon is one of immense, relentless pressure. With the furnace cycle complete, the aluminum ingots are freed from their molds and moved into a preheating chamber. This process softens the metal, bringing it to the perfect state for rolling. Once ready, each ingot is fed between massive, counter-rotating steel rollers. Tremendous force immediately flattens and elongates the block, beginning its radical transformation from a thick slab into a thin sheet. The process repeats across multiple roller stands, with the gap between each pair narrowing progressively. A block that began several inches thick, often over 8 to 10 inches, is gradually compressed into a uniform metallic plane. To manage the intense heat generated by this friction, a fine mist of water constantly sprays the surface, preventing cracks or warping from the extreme stress. By the final stage, the sheet reaches its target thickness, sometimes just a few hundredths of an inch. It emerges as one continuous strip, which is then guided forward and tightly wound into enormous industrial coils. These standard, semi-finished coils are now prepared for subsequent processing, such as cold rolling, cutting, or stamping, depending on their ultimate application. From a vast, gleaming river of metal, a familiar shape begins to emerge. The aluminum can itself is a testament to the power of this cycle, capable of returning to the shelf in an entirely new form within just a few weeks. The journey begins as thin aluminum sheets, unspooled from massive coils, are stamped into countless flat, round discs known as blanks. Each blank is then driven into a deep drawing press, where one powerful stroke instantly forces the metal into a shallow cup with thin walls and a flat base. This cup then passes through a succession of ironing dies. With each stage, the aluminum is stretched ever taller, its walls growing thinner until the can reaches its final dimensions. The top edge is then carefully narrowed, forming the neck that will accept the lid. Inside, a microscopic polymer coating is sprayed on, creating a crucial barrier between the metal and the liquid to ensure both safety and flavor. A flash of color then adorns the exterior, as high-speed rotogravure printing applies precise labels to thousands of units per minute. Completed by the thousand, the cans are stacked in gleaming batches, now prepared to enter the filling and sealing lines. From the roar of the factory to the quiet of a refrigerator shelf, its first life is a short one. These vessels soon appear everywhere, neatly stacked on store shelves, submerged in ice at a bustling cafe, or passed between friends at a summer barbecue. Each day, the world consumes hundreds of millions of them, woven into the unspoken rhythm of our lives, marking everything from a brief moment of refreshment to a shared celebration. Yet, the can's true value is revealed only after it's empty. At this moment, it arrives at a crucial turning point. One path leads to a landfill, the other to a near-infinite cycle of rebirth. Where deposit return systems are in place, over 80% of these cans are recovered, transformed, and returned as new products in just a few weeks. By contrast, a can discarded with common trash becomes a lasting environmental burden, squandering the potential of one of the most sustainable materials ever engineered. Ultimately, the fate of this material rests in the hands of the consumer. Placing a can into a recycling bin is the critical act that keeps the cycle alive, ensuring this metal continues its endless journey instead of meeting a wasteful end. Its journey has no true end, only a series of new beginnings. We have followed the path of aluminum's remarkable rebirth, a closed-loop cycle that transforms what seems like worthless scrap into an infinitely reusable resource. From this process, the metal emerges once more, ready to become anything from a simple soda can and a sturdy window frame to the vital components of an aircraft. This circular journey is more than a feat of modern engineering. It is a direct reflection of the choices we make each day. The can held in a hand can either become landfill waste or, in just a few weeks, return to the production line, ready to be reborn as something entirely new. The decision rests on a single, simple action, placing it in the correct recycling bin. So the question remains, will its life end abruptly, or will we help it continue an endless journey, contributing to a greener future for us all?